Hello everyone, welcome to another live session for the online astronomy course. Ready to take your questions.
So our first question is from Hazem Faraj, who is on with us live, who asks, can quantum computing contribute to the discovery of parallel universes and prove the idea of a multiverse?
Wow, okay, that's a heady question for the first one. So just to the scientific part of that, the multiverse idea, and that's still considered very speculative in the realm of cosmology. The idea emerges from two things. One, a conventional outcome of the Big Bang model is that the physical universe, all of space and time, is larger than the universe we can see, the observable universe. So there are definitely regions of space and time potentially filled with galaxies and so on, dark matter, dark energy, that we can't observe, even in principle, because of the speed of light limitation. To go beyond that and imagine not just that there are regions of space and time we can't observe, but there are other entire universes of space and time, relies on the fact that the universe emerged as a quantum event. So where the laws of physics run aground, because we haven't tested the merger of the four fundamental forces, is in the first tiny fraction of a second after the Big Bang. And if the supposition that the universe was originally a quantum state, or emerged from a quantum state, maybe as a quantum fluctuation, is correct, and that seems to be a fair bet, then hypothetically there may have been other quantum states, other regions of space-time beyond our own that emerged into their own universes, perhaps with different properties from this universe, hence the multiverse idea. So the question becomes, how do you test the multiverse idea? And the answer is we don't have any direct test of it, because we're limited observationally to the use of light and other indirect measurements of what happened a long time ago, and there's no probe at the moment to test for multiple universes. Whether quantum computing or sort of quantum phenomena that we do control in terms of our technology can help in this is completely unclear, and it's unlikely, actually. Quantum computing is going to help with the calculations that cosmologists do all the time, and some of those calculations that revolve around understanding the early state of the universe do require enormous computational power. So in that indirect way, quantum computing will help understand early universe situations, but not in any direct way of testing the multiverse idea.
All right, our next question is from another live viewer who asks, what was there before the Big Bang? Does the Big Bang have its origin in quantum fluctuations in a previous universe which experienced a heat death?
So the conventional Big Bang model is an explanation for what happened to the universe from a tiny, hot, dense state. And the conventional Big Bang, which is very well tested and is a fairly robust theory of science, is mute, or says nothing about what caused the expansion or what was there before the universe that we live in existed. So the simple answer is no, there's no supposition or testable prediction for the universe before the Big Bang, or from which state the universe emerged. There's plenty of speculation, plenty of theorizing, but at the moment I'm an observer, so as an experimental scientist, I like to, base these things on evidence. There's no evidence to guide us in talking about this state.
All right, the next question is from a live viewer who asks, given the accelerated pace in exoplanet discoveries, do you think that the Drake equation should be revised? And then when do you expect first contact will happen?
So exoplanet research is definitely recasting our understanding of the Drake equation, in the sense that the first three terms of the Drake equation are pretty well known now. We know the rate at which stars form. We know pretty well the average number of planets per sun-like star, and we're getting a pretty good handle through Kepler on the number of habitable planets per star system. So those numbers are pretty well determined. And the big unknown, and all the unknowns that follow in the Drake equation, revolve around biology. So until we can do life detection experiments on Earth-like planets, that's not that far away, maybe 5 or 7 years, we won't know about the second part of the Drake equation. So some people have recast the Drake equation, essentially cutting it in half, where the first half is really astronomy numbers that are being measured better and better as years go by. And the other half is the part that talks about biology and of course, in the end, culture and sociology, when you talk about how long an intelligent civilization can survive. So that's a simplistic way of dividing the Drake equation to basically the things we are learning very well and the things that still are very unclear. The contact, the idea of contact is far beyond our current capability because we're approaching a realm of being able to detect biology indirectly on Earth-like planets, probably tens of light years away. But we will know very little about that life. It will be the simplest detection using a spectrum, an overall average spectrum of reflected light from a habitable planet that indicates the presence of biology. It won't tell us the genetic nature of that biology, whether it's the same genetic code as ours, whether the life has gone beyond microbial to be larger forms of organisms. So we'll still be pretty ignorant about that. But it's still a very rapid rate of progress compared to where we were 10 years ago.
All right, our next question is from Nightingale, who's on with us live, who asks, how do astronomers and astrophysicists analyze the spectra of stars accurately while accounting for any interstellar matter that could be between us and the star?
So interstellar matter is an important feature of dealing with starlight from distant regions of space because although the vacuum of space is an almost perfect vacuum, the mean density of interstellar material is about 1, maybe a little less than 1 atom per cubic centimeter. Now the air you're breathing has 10 to the 19 or 10 billion atoms per cubic centimeter, so it's a fantastically good vacuum. But when observed over enormous distances, tens or hundreds of light years, that amounts to a path through a significant amount of material. Most of that material is hydrogen and helium, the two most abundant elements in the universe, but the significant amount of it is also tiny microscopic dust particles that emerge out of the winds from stars that are the material out of which eventually planets are made. So there's a thin gruel of interstellar material that's gas and dust. And when we look through that, that has an effect on the starlight traveling large distances. The two main effects of especially the dust are to dim and redden the light. And the more the material or the larger the distance we look, the redder and dimmer the light. Now, neglect of this interstellar material in the 1930s led some astronomers at the time to grossly miscalculate distances to objects because the distances, of course, were fainter due to the dust, not because they were intrinsically faint. So astronomers attributed them to being further away than they actually were. So you can make a big mistake if you don't take into account this obscuration, as it's called, from interstellar material. It's been pretty well mapped out now. That was almost 100 years ago that we became aware of this issue. And so people now can measure the amount of dimming and reddening and correct for it, and so correct for that sort of veiling effect of interstellar material. But there's no escaping it. The further away you look, and especially if you look through the plane of our galaxy, then that material is affecting the light of every star you look at.
All right, the next question is from Eric, who's on with us live, who asks, would it be worth it to set up a mining operation on the moon, on site, or transporting it to Earth? What minerals could you mine, and what do we need to think about, and what are the main difficulties?
So for mining on the moon, the technology is advancing to make that a really going proposition. And I imagine in practice, this will be a largely robotic operation. The difficulty and expense of being on the moon involves people and keeping them safe and fed and clothed and housed and protected from cosmic rays and so on. If you have a minimal human presence, maybe just an occasional human presence, but largely do the work robotically, then you can essentially set up mines and factories on the moon with existing technology. In fact, you don't have to ship most of the equipment there at all. There are methods to take the lunar soil and using electrochemical methods to turn it into building materials. You can use 3D printer technology, which means you basically send 3D printers to the moon to fabricate the pieces that you need to make a factory or or a mining operation. And so you wouldn't have to carry all your stuff there. You'd also be able to use the lunar soil to get water. If you didn't need to support a human population, you can get oxygen and water from the lunar soil. So lunar mining in a largely robotic way, automated factories, is pretty close to being possible. Now, what would you mine, and is it worthwhile? Because it's obviously a lot harder. You know, mining on the Earth sometimes is expensive, takes place in remote situations or miles underground, and is difficult and hazardous and expensive. But the moon is a much more austere and rugged environment, and it's, you know, 250,000 miles away. So it would have to be something pretty valuable, something not either that you couldn't get on Earth or existed in such abundance that you had to go to the moon to get it. The thing that people have got their eyes on the moon is helium-3, isotope of helium, that is obviously important if you wanted a nuclear reactor, for instance. Helium-3 is very rare on the Earth, but it's actually created on the moon's surface by interaction of cosmic rays with the lunar soil. So while it's a very rare isotope on the Earth, it's less rare on the moon and could sort of be harvested on the moon and sent back to the Earth. So that's one thing people have talked about. But the lunar soil, if you look in the right places, also has rare earths and minerals that have quite a high dollar value on the Earth. You know, their value per ounce is high. Is still a lot of expense to get such material. So even assuming you've mined it, you have to send it back to the Earth. You have to launch it from 1/6 gravity. That costs rocket fuel, and you have to land it on the Earth safely. More rocket fuel required for that. So it's not clear that it's economically viable at the moment. But people have made fairly sophisticated plans for mining on the moon and showing that it might be economically viable maybe in 10 or 20 years. If you had a lunar elevator, a space elevator on the moon, then that would remove the rocket fuel cost, because you could essentially haul your materials or mined ores off the surface using solar energy, and then you get them into zero gravity and take them back to the Earth. So people are thinking about that as well, also on a time scale of maybe 15 or 20 years. But this is probably going to happen at some time in our lifetimes.
All right, the next question is from a live viewer who asks, is the curvature of space-time near a massive object the same as the general theory of relativity, or are they two different concepts?
No, the curvature of space-time is defined by general relativity. That's actually what the equations of general relativity do. The equation on one side has the density of mass and energy in some region of space, mass and energy being equivalent according to Einstein as well. And then on the other side of the equation has the curvature of space-time, defined in a fairly complicated way in terms of manifolds, which are sort of geometric spaces that actually can be more than three-dimensional in some situations. So yes, the curvature is very directly defined from the equations of general relativity. If you have a massive object like a black hole, or just a massive star or galaxy, pretty much anything with a lot of mass and a lot of gravity, general relativity will calculate what the curvature is, and that curvature calculation will predict how much light would be bent or deviated when it passes near such an object, dictates the trajectory of any object in the proximity of a large amount of mass. And that theory, of course, has been tested in weak gravity situations frequently over the past 100 years, and in strong gravity situations been tested in the last 20 years, and so far it's held up pretty well.
All right, the next question is, what are your views on the concept of a single unified theory suggested by people like Stephen Hawking?
So it's a goal of physics and astrophysics, and has been essentially for close to 100 years since the quantum theory was developed. So relativity was our best theory of gravity, stems from 1916, of course, was published then. The quantum theory was developed in the 1920s and 30s. And for decades afterwards, these two theories did not seem compatible. The large-scale theory of space-time and mass energy deals with these big situations of the universe. It's a smooth theory, a geometric theory, whereas the theory of microscopic particles and subatomic matter is a grainy theory, a quantum theory. And they really describe nature very differently. So it was known that it was going to be a big challenge to somehow combine or merge these two theories. In the modern thinking, this merger or unification of these theories happened naturally in the universe itself when the universe was tiny and small, near the Big Bang. Because as the temperature and energy increase, then the coupling constants of the forces of nature become the same, and so you end up with one super force instead of the individual forces, which have quite different strengths in the large and cold universe. So that's what people think happened, and so that suggests a test somehow in the Big Bang itself. But the theory of what it looks like to combine these two very different great theories of nature has thwarted the greatest physicists. Einstein worked on it for 20 years with no real substantial success. Hawking worked on it for 10 or maybe 15 years, taking different approaches, and again, didn't make any real headway. I mean, he had some interesting ideas, but no unified theory emerged out of that. So while people talk about quantum gravity, that's a sort of catch-all phrase for the merger, the unification of these two great theories. There is no single theory of quantum gravity that is thought to be correct or even really testable. And it remains one of the most important issues in physics to find such a theory.
All right, the next question from a live viewer, Cecil, asks, what is Sagittarius A?
Sagittarius A, or to the radio astronomer, Sagittarius A star, because it has a little asterisk next to it, is the radio source at the center of our galaxy. And so when people were realizing that the center of our galaxy contained a pretty extraordinary situation, the way they learned that was by radio methods. If you look towards the center of our galaxy in the Sagittarius constellation, you just look by eye, or it's mostly in the southern sky, you can't see to the center of our galaxy. Referring to the earlier question of interstellar matter, the interstellar matter between us and that point, which is about 27,000 light years away, there's so much interstellar matter that it's like looking through a closed door. Basically 1 in a billion photons reach us, optical photons reach us from the center of the galaxy. But the obscuration that dims and reddens visible light, its effect diminishes with increasing wavelengths. So for radio waves, far longer than visible waves, there's essentially no effect. So the galaxy is transparent to radio waves. And so as radio astronomy matured, radio astronomers were able to look towards the center of the galaxy clearly and unimpeded. The second thing radio astronomers did was combine their telescopes with interferometry, and that let them get very sharp images, super sharp images, sharper than any optical image. And as that technique matured, radio astronomers realized in the 1980s or 70s and 80s that there was an extremely compact radio source at what we would think of as the center of our galaxy. That's the center of the mass of all the stars that pile up in the center of the galaxy. And it was called Sagittarius A star. And as the techniques got better and better, the limits on the size got smaller and smaller. So it is still the most compact radio source known. It's not a super powerful radio source. It's nothing like the power of the radio galaxies like Cygnus A and Centaurus A and these other galaxies in remote parts of the universe. But it's very interesting because what could make a radio source that compact? And over time, people realized that Sagittarius A, this super compact radio source, was essentially marking the location of a 4 million solar mass black hole. Now, the black hole itself, of course, is not visible. The event horizon shields that mass from view. But all the orbits of the stars near Sagittarius A, their super fast speeds and their tight orbits around what seems a very compact mass, suggest a black hole. So Sagittarius A is essentially the marker in radio astronomy for the black hole at the center of our galaxy.
All right, the next question is sort of related. What is the nearest black hole to Earth, and what are its dimensions?
So the nearest black hole to the Earth, it changes from time to time in terms of the remnants of dead massive star corpses that are black holes. So a star that started its life as 10 or 15 times the mass of the sun and would die and leave behind something 3 to 5 to 7 times the mass of the sun. That fits the definition of a black hole. There are probably 3 dozen good black hole candidates, and the nearest of these is about 130, maybe 150 light years away. So that's not to say there aren't black holes potentially closer than that, but the black hole candidates, only a few dozen of them that have the best evidence that they really are black holes, are all in binary systems. That's how we measure the mass of the black hole by its effect on a visible stellar companion, is about 130 light years away. And black holes are quite rare. There are very few stars massive enough to make a black hole. So we would not anticipate, even though we can't rule out a black hole closer than that, based on the statistics of star masses and how they die, we really wouldn't expect a black hole much closer than 100 light years away.
And our next question is, are there concerns about what might happen in a few years with all of the space junk orbiting the Earth? Are there plans for a response in case it should rain down on us?
Yeah, space debris or space junk is a huge problem now in the space industry and in the efforts for us to live and work in Earth orbit. So over time, over the 60 plus years of the space program, thousands, tens of thousands of satellites have been put up there, and then some much larger objects like the Hubble Space Telescope and the International Space Station. And over time, some of those objects have been hit by, they had space junk hit them or meteorites hit them, and so they've destructed, or they've just fallen apart, or they've occasionally collided with each other. That's actually quite unlikely, because even that crowded area of space junk is still quite empty space. And then famously, the Chinese actually blew up one of their own satellites and made a lot of space debris, which is a very antisocial act. So space junk is a real problem. There are just a lot of pieces of metal up there, and some of them have turned into many, many pieces of very small metal. And all of that debris is moving at thousands of miles an hour. So when it hits a more stationary object or an object moving the opposite direction, it's a devastating impact. In the case of the space station, for instance, when any piece of space debris much larger than a grain of sand or a very small pebble is known to be in the vicinity of the space station, luckily we can measure these things, the astronauts pretty much have to hide. They have to go into the most secure central part of the space station. That's what a danger it is if there are people up there. Most of this debris is in what we'd call low Earth orbit, so it's between 200 and 100 and maybe 150 and 250 miles. The Hubble Space Telescope and the International Space Station, the most valuable hardware we have up there, they're in low Earth orbit, but a high low Earth orbit, so 250 to 350 miles. So they're away from most of the debris. But where most of the satellites go, it's getting pretty crowded with junk. The remedy for this, it's really not obvious, because it's really hard to clean up the junk. As I mentioned, the space between the pieces is still pretty large. It's not like you can scoop them up or sweep them up. But there are some interesting ideas to use sort of electromagnetic scoops, not a physical scoop, but something that's created by an electromagnetic field that spans maybe hundreds of meters or a kilometer, and use that to sort of sweep up the junk and sort of do a sort of vacuum cleaner type deal on the orbit. But even then, the region you're looking at is so large, it would take decades or centuries to make a significant impact on it. So at the moment, it just stands as a really big problem. Once you've got the debris up there, it's really hard to get rid of it. As for it being a hazard, that's not anything that we really worry about. Famously, the small Chinese experimental space station deorbited and, could have, I suppose, in principle, hit ground and kill people and cause some damage. But most of the space junk is so small that when it slows down by drag in that very thin upper Earth atmosphere, those pieces essentially just burn up as they fall through the atmosphere. And they're so small that they essentially they'd aerobrake as they came into the thicker atmosphere and really not cause a major problem. So there's no hazard to humans or us from that space junk, but it's a huge issue for the space industry.
Right. Our next question is from a live viewer, Isaac, who asks, is the Earth really getting closer to the sun, and will it one day be engulfed in flames and burn up, or is that just a rumor?
So there are effects, there are subtle gravitational effects from a normally stable orbit, and the Earth's orbit of the sun is a fairly stable, long-term stable orbit. So the Earth's position relative to the sun is not going to change substantially literally for billions of years. It's been orbiting the sun for 4.5 billion years, and in another 4 or 5 billion years the sun will die, and even then things won't change very much, except the sun will lose mass, and that will actually change the Earth's orbit. So until that time, the changes to the Earth's orbit are minuscule. Now, in principle, there's a gravitational effect, gravitational drag effect, that does lead the orbit to decay. So if it's going to change at all, it's going to change in the sense of going towards the sun. But basically, the Earth is not going to do that before the sun itself dies, and then it's sort of the end of the life on Earth and the end of the solar system as we know it anyway.
Right. The next question is from Maria, who asks, if there is no center of the universe, where or what is the region where the Big Bang occurred?
So this is a confusing concept for people thinking about cosmology, but the Big Bang essentially is everywhere, because every part of space and time, including our part of space and time where the Milky Way is, but also remote parts of space and time where distant galaxies are, was part of the Big Bang. We're all part of one universe. And every part of the universe has been moving away from every other part of the universe in 3 dimensions. And they were all part of this same singularity or initial event. And so there is no location of the Big Bang. I mean, we could call ourselves the center, or some on a distant galaxy could call themselves the center. And the evidence for this is the microwave background, this radiation in microwaves of almost perfectly uniform intensity or temperature in every direction of the sky, uniform to about 1 part in 100,000, is the same in every direction as an indication that we're all embedded in a bath of radiation left over from the Big Bang. And once again, some citizen or denizen of a distant galaxy would observe exactly the same thing and would draw the same conclusion. So since every galaxy was part of this expanding space-time situation that started with the Big Bang is manifested everywhere the same way.
Right, our next question is, how did Jupiter get so big in comparison to other planets in our solar system?
So Jupiter, as the giant planet, it's worth remembering that when we call it a giant planet, and it is the biggest planet, it's 1,000 times less massive than the sun. So the first reference point on a giant planet like Jupiter is that if you put Jupiter together with all the other planets and all the other space debris and the moons of the planets, it's still a tiny fraction of the mass of the sun. So really, planets are very small compared to stars. Jupiter, Saturn, Uranus, and Neptune all are gas giants, so most of their mass is in hydrogen and helium, and they're a lot bigger than the Earth, but they're all inferred to have rocky cores. So the common feature of the solar system planets is that they all have rocky cores. In the case of the Earth, and the Earth, Mars, Mercury, and Venus, those rocky cores have attracted atmosphere. Actually, Mercury is not massive enough even to have an atmosphere. But the bulk of the planet is in a rocky mass. For the outer planets, at the formation stage, they also have those rocky cores, probably bigger than the Earth. Their guesses or best estimates are 3 to 5, maybe 10 times the mass of the Earth. So they're sort of super Earth cores. And then as the material in the solar system condensed and cooled, those massive rocky cores were able to accrete material, the cool gas that was remaining in the disk that formed the solar system, and that's mostly hydrogen and helium. So over time, those rocky cores attracted mantles or surrounding atmospheres of hydrogen and helium that dominates their mass. This process, it's not clear, but simulations suggest it took only 30 or 40 million years, quite fast. Sort of less, 30 or 40 million years out of a 4 billion year history. And we think that's a general characteristic of planet formation, that outer planets far from their star will be able to accrete more gassy material and so be giant gas giants like Jupiter and Saturn, whereas inner parts of solar systems, that gas, because those regions are hotter and there's less gas available in a smaller region, those planets just tend to be more rocky with slight amounts of atmosphere.
All right, the next question is from a live viewer who asks, what do we currently know about antimatter and what is the future of research on antimatter?
So antimatter is a fundamental aspect of physics, the idea that in quantum theory, every particle has a counterpart with opposite quantum properties. In the case of electrical charge, it's obvious. The positive charge turns into a negative charge, but the other quantum properties are opposite as well. So in that sense, it's sort of like mirror matter. Antimatter is mirror matter. And so every particle will have an antiparticle. That's just a part of standard physics. And if particles and antiparticles meet, they annihilate to create pure radiation. So they essentially disappear to create pure radiation. And because in microscopic physics, all physical processes are reversible, if a particle and antiparticle meeting can create pure radiation, then if you have sufficient pure radiation, you can create a particle and an antiparticle pair, and they will fly off in opposite directions. And that's how you make antimatter in the laboratory. And so antimatter was first observed in the early 1930s, I think. Positron, Anderson, the physicist John Anderson, won a Nobel Prize for that discovery, that antimatter was real. It was predicted by Pauli, one of the pioneers of the quantum theory before that. So it was one of the great predictions of quantum theory and then subsequently observed. I think that discovery actually was in the 1940s. And all the other antiparticles have been detected too. So for the electron, the positron, for the proton, the antiproton, for the neutron, the antineutron, quarks, antiquarks, etc. And so it's not hypothetical, it's real. It's rare, of course, because the universe is overwhelmingly made of matter. So in a sense, when the universe was born, there was a sort of cosmic coin toss where, although in the very earliest stages of the Big Bang, there was equal amount of matter and antimatter born out of the intense radiation of the Big Bang, there was a very slight asymmetry in the amount of matter and antimatter. And as the matter and antimatter annihilated early in the history of the universe, a small residue was left over of matter, and that forms the material content of the universe. And then there's a lot of radiation too. There's actually a few hundred million photons for every particle of any kind. So the universe has more photons than particles and has very, very, very few antiparticles. They can only be created through technology, essentially. CERN is the biggest factory for antimatter because it has part of its work, in fact, most of its work involves colliding particles and antiparticles by sending them opposite directions around a ring defined by magnetic fields and using the collisions to create debris and new particles like the Higgs boson and so on. So that's the best way of making antimatter as an accelerator. But I think I read an article out of CERN that calculated that the most CERN could ever make, if it worked really hard on it, would be something like a picogram of antimatter. And the cost of it in terms of just energy cost, electricity cost, would be billions of dollars. So this is probably the most valuable commodity or substance known in the universe.
All right, our next question is from Ryan, who's on with us live, who asks, why does frame dragging occur? How does a nearly perfect spherical body rotating actually twist space-time around it? I understand how a turning ball in water could turn the water via friction, but how could this happen with space?
Well, it's a good question. It's a basic prediction of general relativity that frame dragging occurs. And in a sense, it makes sense because the general theory of relativity directly couples, that's the nature of general relativity itself, it couples the mass energy state to the curvature of space-time. So if that mass energy state is dynamic, moving, rotating, spinning, then that couples to the curvature of space-time too, and in a sense of drag, like you would imagine in water swirling around a sinkhole, the space-time frame is dragged and precesses essentially around a spinning object. And this effect has been not directly, but it has been indirectly observed, so it does appear to be a real phenomenon. And it's actually a kind of clever way. If you can measure the dragging effect, it's of course another test of general relativity. Gravity Probe B was able to test the frame dragging, and it was actually the first experiment in the 1980s. It wasn't published until maybe 7 or 8 years ago, actually. But Gravity Probe B showed that frame dragging actually occurs, using the Earth as the example.
Right, our next question is, what kind of discoveries do you expect now that gravitational waves have been observed?
So we should expect a whole new era of gravity wave astronomy. As LIGO moves into its current or its proximate phase of taking data, it went down for a while, went down for over a year to have increased sensitivity and wider detectors and various enhancements. Back online, it's in a mode where it should be detecting gravity wave events roughly 1 a week. So physicists pretty much anticipate dozens of black hole merger or neutron star merger or black hole neutron star merger events per year. At the moment, we just have a handful. We have 3 strong events and a weaker event that was considered marginal. But this is going to turn into an industry. It's going to consume the gravity wave researchers, of course, but it's also going to consume a lot of astronomers' time, because when neutron stars merge, as we know, creates visible signatures or electromagnetic signatures. And so as optical astronomers can do something, X-ray astronomers can do something. So it's going to be a whole industry. Black hole mergers are still going to be quiet as far as electromagnetic radiation goes. So the black hole mergers can only be measured by the gravity waves themselves. Meanwhile, there are other gravity wave detectors coming online. The Virgo detector, not quite as sensitive as LIGO's twin detectors, is online and been online for a year or so. And both the Indians and the Japanese are bringing gravity wave detectors online. So all of these instruments working together, they won't increase much the number of events detected, because LIGO is still the most sensitive part of the array. But they will increase dramatically the amount of information we can squeeze out of every measurement, and also the localization or the determination of which region in the sky the gravity waves came from.
Right, our next question from a live viewer is, what is the contribution of Hawking radiation to modern day cosmology and astrophysics?
Hawking radiation was one of the main predictions of Stephen Hawking's work on black holes in the mid-1970s. The archetypal black hole has only 2 properties. It has mass and it has spin or angular momentum, because the star that forms black holes were spinning, and so the black holes themselves are spinning. In theory, black holes might have electrical charge, but it's considered that most matter on the scale of a star is electrically neutral, so it's unlikely that black holes have charge. So black holes are very simple. Black holes have no hair. That was the colloquial phrase about that. Hawking's theory suggested that black holes have a thermodynamic property where they have a temperature. Because every object in the universe, other than a black hole, has a temperature. And so in his theory, black holes have a temperature. It's a very small temperature. It's nanokelvin, 10 to the minus 9 Kelvin or so for a solar mass black hole. And that, of course, suggests that if the black hole is radiating energy and energy and mass are equivalent, then the black hole must be losing mass, i.e. evaporating. So the prediction of Hawking radiation is also a prediction of black hole evaporation, very, very slow evaporation. So this is really one of the things Stephen Hawking became famous for. But that temperature that I mentioned, a nanokelvin, that's undetectable. The black holes we know of are in complex, messy situations with a companion star and lots of complex astrophysics going on. And so the ability to measure that incredibly small temperature of the black hole is beyond current technology, and some people think it may never be measurable. So to prove Hawking's theory, we're going to have to use other more creative methods.
All right, the next question is from a live viewer who asks, I have heard the Higgs boson being described as a field. Can you explain this? And then, does this field cover every square millimeter of the universe, or would it be confined to just a small area, for example, like an atom?
Right, that's a good question, because people talk about the Higgs boson as the other word that is called the boson is a particle physics designation for something that obeys both Einstein's statistics, like photons, has integer spin in quantum states. But the real distinction is that a lot of people colloquially call the Higgs a particle, and then, as this question suggests, other people refer to it as a field. So to a physicist, and in physics terms, it's more accurate to call it a field. The Higgs particle is not really a single isolated particle, so you can visualize something's moving through space at a certain speed and being localized. It is more accurate to think of the Higgs phenomenon as a field, and that field extends over large distances and indeed potentially permeates the entire universe, because the Higgs is just the mechanism by which things attain mass. So what is a field? Well, our best analogy, of course, is electromagnetic fields, electrical fields or magnetic fields. So something that has a attribute where it changes the behavior of particles, say, moving through that field. So charged particles moving through an electrical field behave in a particular way because of that electrical field, and that tells you about the distribution of that field. Well, in the Higgs analogy, the Higgs field is an entity that pervades space, and it provides particles, or it gives particles their mass as they move through it. So you could think of the analogy, as people say, is that the more massive particles like protons or quarks are more viscous just because of the quantum way they behave with this field, and so that viscosity or drag means they have more inertia and so have higher mass compared to, say, an electron or a neutrino. But it's that same Higgs field permeating space and time that attributes mass, or gives mass to all the particles we see. Now, that's not a full explanation, because even though the Higgs field has been measured by CERN, and it has a characteristic energy, about 130 giga-electron volts, that was the great discovery of CERN 4 or 5 years ago, nobody really knows why the Higgs field has that particular energy. It could have had any of a big range of energies, and actually that's rather low compared to the energy expected from a lot of fundamental theories. So all the puzzles and understanding of Higgs phenomenon is not complete yet.
Right, our next question is, what was the main problem with the 1976 Viking experiments searching for Martian life? I know that the results were debated and not conclusive. And then what about the Allen Hills meteorite conclusions?
So let me divide those into two questions. So the Viking experiments, Viking were very far ahead of its time mission from 1970s, mid-1970s, conceived of in the late 60s, actually. It took a while to get there and to build. So twin Viking landers, there were the Viking orbiters that released twin landers that went to different parts of Mars. And they were essentially twin spacecraft and twin landers. And they did a series of experiments, scooping up soil on Mars in the places they landed, and subjecting it to simple experiments. And the experiments were designed to potentially test for the presence of life. Remember, these were technologies, now 50-year-old technologies, in small packages that had to be sent very large distances through space. So it's kind of amazing they could do that at all back then. So these were not as sophisticated as the experiments we would design today, and partly for that reason, the results were ambiguous. However, formally, 3 of the 4 life-detecting experiments declared null results, which is to say they did whatever they did, showed no evidence of life. And what they typically would do would be to scoop up soil and add nutrients to it, where if that was a terrestrial soil, then we'd see metabolic activity from microbes in the soil. so they didn't see that. Another important experiment took soil and put it into a furnace and essentially baked it or boiled off whatever volatile material or gas might have been bound into the soil to try and measure if there was any hints of biology there. And also nothing was seen. So 3 out of 4, pretty much no results. The fourth was very inconclusive though, and this was called the wolf trap experiment. And Gil Levin, who was the PI of that experiment, he's now in his mid to late 80s, he has sort of been steadfast ever since that his experiment might have detected life, that his result was very ambiguous, and ambiguous maybe in the direction of indicating some metabolic activity due to microbes of unknown function and form, because the experiment couldn't measure that. And if you go back and, as I have a while ago, read the original Viking report, the final report of the Viking experiments, the language is very measured. It's very carefully measured to make it clear that the results were a little inconclusive. And so the ruling out of life on Mars by the Viking, that was not what Viking did, really. It maybe leaned in that direction, but it was not a super strong result, leaving the door open for a new generation of experiments. Now, that's not going to happen from Curiosity, the current large Mars rover, because Curiosity really wasn't designed around life detection. But the Mars 2020 rover, its identical twin, just made with extra hardware left over from building it, is going to have some life detection experiments. And really, that'll be the first time, an awful long time after the Viking experiments, that we've done Martian life detection. And the second question about the Allen Hills meteorite was, Allen Hills meteorite was a Martian meteorite that was found, I can't remember its full chronology, but it was blasted off Mars a long time ago as an old rock, an ancient rock, 3+ billion years old, floated through interplanetary space for millions of years, tens of millions of years actually, and I think landed on the Earth 40 or 50,000 years ago. I'm not sure of that exact number. And then it was discovered by scientists on the pristine Martian ice, where meteorites are really obvious because they tend to be dark, charred rocks, and the ice is very pure and smooth there. So it was discovered. It was considered to be in fairly pristine condition. It was obviously at impact, it went down into the ice some distance. And, a series of scientific experiments were performed on this meteorite. It was unequivocally from Mars because within the rock, there are tiny little, air bubbles or bubbles of vapor that are sealed by the rock itself. And though when they were taken into the lab and analyzed in a vacuum, the air trapped in the Martian rock matched the Martian air measured by Viking and other landers. And the geology of the rock also indicated Mars. So there was essentially no doubt that it was a Martian rock. The evidence for life, though, was always vague and uncertain and ambiguous. The chemical evidence for life was just not there. The morphological evidence, these tiny little forms that look like microbes, they were much smaller than terrestrial microbes, and just the presence of those sort of shapes is not conclusive, because people showed that you could have rocks and smash them together and the splatter pattern would look like those microbes. So that was probably the most interesting evidence when you saw a picture of it, but it was the least convincing to a scientist. The only ambiguity left decades after that rock was analyzed is there were magnetic particles found in that rock. The magnetic forms of life, or sort of every form of life in the tree of life, uses magnetic fields, down to bacteria themselves. And so there were an analysis done on the magnetic particles in that rock that suggested forms and depositions that mirrored microbial use of magnetic fields on the Earth. But that wasn't enough to convince most planetary scientists. So the verdict that came in on the Allen Hills meteorite was no convincing evidence for life inside that rock.
All right, we're going to do 2 more questions. The first one is, can you give a brief explanation of the black hole information paradox?
Right. So yeah, there's either the book length version or the brief version. So the black hole information paradox stems from an issue in quantum physics, which is that in particle interactions, information is preserved. So when particles interact or change into other forms, or particles come together and collide and new particles emerge, their quantum properties are conserved in the sense that, so the information of those interactions is not lost after an interaction or collision or antiparticle exchange or anything like that. And so that's a phenomenon of quantum physics that's held. It's very high regard physical theory, and it's been proven in the lab and in accelerators. Well, when you get to a black hole, you have an interesting situation, because the matter that goes into a black hole, that formed the black hole and may continue to fall into it, is lost from the world. It cannot communicate with the world. There's no information that passes through the event horizon. And so the information that is always conserved in physical particle interactions seems to be violated in a black hole, because the information is lost. In the most trivial sense, imagine you just toss an encyclopedia into a black hole. Well, that encyclopedia had a lot of information, and when you toss it in, you can't get that information out. It's lost forever. And so the loss of information in a black hole, which seems to violate a very fundamental rule of quantum physics, is the paradox. And the resolution of the paradox, in some people's eyes, is that that information isn't totally lost. And so one of the ideas, which is probably also known to people colloquially as the holographic principle of black holes, is that somehow as the matter falls into the black hole, the information in its particle states is actually somehow preserved at the event horizon, or essentially written onto the event horizon in the way that a hologram can be used to reconstruct a three-dimensional object by shining light on it. So that's the holographic principle, and that stems from the information paradox. It's a way of sort of getting around the paradox. But then that's not a simple resolution either, because when you go through the quantum calculations, you end up with something called a firewall, which is a place just outside the event horizon where the information appears destroyed in a torrent of energy anyway. And so again, the information seems to be lost. So this is a huge issue in black hole and quantum physics now, and it hasn't gone away. It was first posed 30 years ago, and it's still a big issue.
All right, and our final question from one of our live viewers is, we know that future Earth civilizations will not be able to access some parts of the history of the universe. So what parts of the history of the universe may never be accessible to us right now?
So the parts of the history of the universe that we can't see are typically the first third of the history of the universe. The universe is about 13.8 billion years old, and so the first third of that chronology is not visible to us, because the universe was expanding so fast during that period of time that those regions of space are not visible to us. And although the universe was decelerating for the first 2/3 of its history, it's now accelerating. And so if those regions of space have not been visible to us in the history of the universe up to now, then they will not be visible to us in the future because of dark energy and cosmic acceleration. So that's a pretty clear demarcation between things that you can see and things that you can never see. And that's straight out of standard cosmology. So that appears to be something we just have to live with. And maybe I'm going to ask and answer the last question that didn't get asked, because this is the first live session since the death of Stephen Hawking. So I will ask and answer the question, why was Stephen Hawking so great, or why is he so celebrated in the world of physics and astronomy? And I'm not going to talk about his personal story, because that's been very well covered, of course, in the media. The fact that he had ALS, and at the age of 22 had a 2-year death sentence, and he managed to outlive that by more than half a century and do great work. Now, in the realm of theoretical physics, most theoretical physicists do their best work in their 20s and 30s. And to be honest, Stephen Hawking was no exception. His most important work was done in the 70s and 80s when he was a young man. And subsequent to that, he was still one of the greatest physicists and very celebrated and knowledgeable and active in writing papers, but he was maybe not quite as at the cutting edge or producing new ideas and new theories as in earlier in his career. But those landmark years of his in the mid-70s to the mid-80s, he essentially redefined the research done on black holes. He made the prediction of Hawking radiation. He showed that the ways in which black holes could and could not be understood. He framed the information paradox very clearly. He pushed gravity theory really in new directions, partly to be able to talk about black holes meaningfully. He addressed the issue of whether black holes had hair, as the phrase goes, or whether they had other properties than mass, spin, and temperature. And he was an active participant in observational efforts to understand black hole properties. He worked with observational astronomers to try and help prove his theories, which of course they're not all possible to prove, and still not possible to prove. He was one of the most original and creative thinkers of the century, and perhaps of all time. Physicists like to make lists of the most famous physicists, and he will probably get the nod in the last 100 years, but he probably doesn't eclipse Einstein, and to most physicists, he probably also sits behind Newton as the greatest physicist of all time. But he was clearly a singular character, contributor. And the fact that he did that in the face of a debilitating physical illness that prevented him from speaking or even writing or doing anything that normal people do for most of his life is really remarkable. So he is definitely missed. Okay, thanks everyone. We'll do this again in a couple of weeks.
And just a quick thank you to the undergraduate students who have been helping us out today. We have Jessica and Carolyn with us today, so thank you very much to the staff. And behind the camera, I'm Matthew. And
yeah, thanks to the crew. We have a crew here, and we also generate a usable product afterwards from this. But maybe I'll talk about that in another session, what we're doing with our FAQ tool. Okay, but for now, goodbye.